Let's start by creating a simple computable property in Volt. As you can see, I've already set up the prefixes we'll be needing for this example. Computable properties are used to test a directed relation between two individuals. Let's create a property that will tell us if one place is south of another place. For this example, we'll be using a PostGIS plugin I've written for Volt to compute the angle between two geographic points. I'm going to name this computable property something that would make sense to see as a predicate in the triple. So I'm going to call it south under the STKO namespace. I'm going to call the azimuth function that I hooked into the PostGIS plugin, which accepts an ordered pair of well-known text strings to compute the angle from A to B. Store that to a variable called bearing. Now we need to define where those well-known text strings come from. We'll grab the strings from the GeoGeometry property contained by each the subject and the object of the input triple. From PostGIS's online reference, the azimuth function, or st-azimuth, returns the angle from A to B as the clockwise deviation relative to true north. I'm going to enter some equations at the beginning of this procedure that will simplify testing if the bearing is within the range that we want to consider south. Finally, I'm going to put a yield statement at the end, and for any execution of this procedure, if the yield condition is true, then this relation, STKO south, will be materialized for that input triple. If the condition is false, however, the procedure will continue until it reaches another yield statement, or until it reaches the end of a procedure, which in this case, since there are no more yield statements, a false evaluation of the yield condition would simply mean that such a relation would not be materialized. Now I can save this source code and compile it to a TTL file, which is the turtle syntax for RDF. As you can see, the compiler automatically inserted the prefixes it needs, along with the ones we declared in the source code. You can see that the root subject of these triples is an IRI that ends with a universally unique identifier. That subject is the individual that represents the definition for our computable property. The Volt Stages property points to an RDF collection, which is essentially an ordered list of the instructions for this procedure. The instructions must be executed in series, so they are referred to as stages. The first stage is an evaluation block, which itself has two unordered instructions, the assignments of the variables heading and spread. These instructions are unordered because the compiler has determined that they will not interfere with each other, so they can be run in parallel. Notice that the assignment of the lower and upper variables are separated into the next stage. This is because they depend on variables heading and spread. Therefore, they are run afterwards to avoid race conditions with the former instructions. Now onto the query stage. These two lines in the source code query for the GeoGeometry property in the subject and object of the input triple. These are combined into a single SPARQL query, shown here serialized in RDF using the Volt ontology. When this is deserialized and evaluated, reserved IRIs such as this subject and this object will be replaced with a variable and possibly complemented by a values block in the SPARQL query, depending on the way the computable property is used. By default, Volt assumes computable properties are not reflexive and will automatically insert a filter into the SPARQL query to prevent comparing an individual to itself. Another evaluate stage shows how the function call to PostGIS azimuth is encoded in RDF. And finally, the yield stage, which is simply a named conditional expression. Now that I've defined the computable property that determines if one place is south of another place, Let's test it with an ask query, which traditionally will either confirm or deny if the query's graph pattern has a complete match in the triple store. For this example, I'm only using DBpedia places in California, and I've also removed the trailing California name from the end of each place's URI for the sake of simplicity. Here we ask, does Yosemite point south towards San Diego? I show the console output from the proxy here, which includes the Sparkle queries that the proxy is submitting to the actual encapsulated Sparkle endpoint. Now that the proxy has tested the SDKO south relation with this triple, we can see the triple materialized, and it is stored in a persistent output graph that is separate from the graph of the triples that it sourced its data from originally. Notice that the proxy also created a provenance graph, which records the origin of the entailment's data dependencies. Since the procedure accessed the geogeometry property of Yosemite and San Diego, a triple for each one of those relations is saved here. If the source graph were to change, and any of those exact triples that were used to make this computation disappeared, then the proxy would recognize that this entire result is no longer valid, a mechanism known as cache invalidation. Asking for a directed relationship that does not hold between two individuals, we see the output graph does not change. If we want to use this computable property in a more powerful way, we can substitute one of the individuals for a variable. Let's select all places in California that are south of Yosemite. And finally, I've updated the computable property definition to declare that it is a type of STKO cardinal direction. With that simple ontological commitment, we can now substitute the predicate itself for a variable and then specify the class of properties we intend to test. And essentially what we've just asked for is the direction from Yosemite towards San Diego, which it returned as south.